So let's have a look at some of the different designs. One of the most simple designs that you can use is what we call a complete randomized design. Now that's a very simple design, and the idea of a complete randomized design is when you have a uniform environment. So in other words, you're not looking at variation in the environment, or it's minimal, and you just want to have a look at your treatment effects. So essentially, you'd have your treatments assigned in a completely random layout in a greenhouse or a growth chamber or something like that. And the assumption would be that the environment is uniform. So you could end up with some of your treatments next to each other on the design, as long as it's random, and you'd lay it out something like that in a greenhouse. There are your treatments, and if you're measuring the height of plants, you'd get a table like this where you have your 4 treatments and your reps, and it would give you an analysis of variance table like this. Now you'll notice there's no rep value there, because essentially you're assuming there's no variation between reps. The environment is uniform. So it's a very simple design, and you'd have your treatments. They're the 4 treatments that I had. The total sum of squares, you'd then remove or the difference between that would be the error. You work out your variance there, you work out your variance ratio or your F ratio there, and it will tell you that the probability is very high that your treatment effects are significant and that they are different. And you'd end up with a means table like this, with your treatment means there, and you can then do some kind of mean separation test like an LSD or a Tukey or whatever you want to do. I'll get to that in a minute. Okay, so this is a trial design that is very simple. It's very easy to construct. The design is easy to analyze, even though sample sizes might not be the same for each treatment. It can be used for any number of treatment. The disadvantage, though, is although the design can be used for any number of treatments, it's best suited for situations where there are relatively few treatments. And the reason I say that is the more treatments you have, the more space you're going to use and the more chance there is of spatial variation. So you want to keep it relatively simple. The experimental units to which the treatments are applied must be as homogeneous as possible, and therefore it's probably more ideal for greenhouse or incubator. But now one of the things you need to also remember, if you're going to look at an incubator or if you're going to look at a greenhouse, I don't know, greenhouse designs vary. The ones that we have in our greenhouse, on the ones, well, you have the roof of glass, you have glass on the one side, and then you've got a wall on the other side where all the control panels and everything else is. And you've got the blowers coming in from the wall side towards the glass. So in reality, your greenhouse is not a uniform environment, unless, like Zach works in some of the smaller cubicles where you can control it a bit better. But if you've got a bigger cubicle. So what happens is you've got a gradient of light from there to there, and the blowers are blowing the cool air in there, and you've got a gradient of temperature from there to there. Okay? So essentially, you're sitting with a variable environment. So when you're looking at controlled environment conditions, also remember to look at the equipment that you are using. And they might not be as uniform as you like to think they are. And I prefer in a greenhouse, especially a greenhouse like ours, if you're going to do a layout of a trial, use something like a randomized block design rather than a complete design, where you're actually putting your treatments in blocks, so that if there is a gradient of an environmental gradient of any sort, okay, you take that into account.